All right, folks, so let us do a quick blitz review over bonding, right? So I think the first place to start will be with types of bonding. So what kind of bonding comes to mind? We have ionic. First of all, what is bonding? Bonding is what? A strong electrostatic force of attraction, right? And so when we're talking about those, about bonding, four ideas come to mind. Ionic, right? Ionic's very strong. We have a metal cation and a non-metal anion, right? And they form a lattice, a crystal lattice, right? Good. Um, Another strong force would be my covalent bonding, right? And this is between nonmetals. And what do? They are sharing electrons, all right? Good. And remember, right here with my ion, we're really not sharing electrons, but electrons at some point have been transferred. The force of attraction is between a positive and a negative here, right? And the force of attraction here is electrons, valence electrons shared by the nucleus, right? Metallic bonding, right? Metallic bonding, this is where we have essentially cations and they are surrounded by a sea of valence electrons. And the reason metals conduct electricity is because these valence electrons are not attached, you might think of, to the cations, but they're relatively mobile since they're surrounded by a sea of valence electrons. These electrons are mobile, which means they can flow readily, and that's why metals conduct electricity. And then covalent networks, covalent networks, and whereas over here in covalent, we're usually only talking about a couple atoms, 3, 4, 10, 12, being bonded together covalently. In a covalent network, you have, large chains of atoms covalently bonded. And we usually think of things like carbon, graphite, diamond, boron nitride, the silicons, right? Silicon dioxide. These are all examples. Now, all these have very high boiling points, high boiling points, high boiling points, because in these three, when we boil, we are actually decomposing. In this case, when we boil, we are not decomposing, right? When we boil, in this case, we are just overcoming IM forces, and we'll get into that more later. Okay, so that gives us a little bit of a background in terms of bonding. So one of the things I think we need to understand is the difference between a polar bond and a polar molecule, right? And this is really talking about a molecular case when we're talking about these bonds and the polar molecules, right? Molecules are just for molecular. So if we take something like carbon and hydrogen, right? And just remind us, right, that they're sharing an electron. And if I have hydrogen, the electrons that are shared are exactly in the middle. So that would be a non-polar bond because there is completely even electrical distribution. But in the case of hydrogen and carbon is pulling on those electrons a little bit more than hydrogen. So you'd have a polar bond. And since the electrons are pulled closer to the carbon, the carbon side of the bond would be partially negative and the hydrogen would be partially positive, okay? So we're talking about a polar bond versus a non-polar bond. If we look at a molecule, we have to ask ourselves, is this evenly distributed? Are the bond polarities, do they cancel each other out, right? So if we look at something like methane, that's a tetrahedral arrangement, and there would be 4 vectors um, of charge pulling in toward my carbon, but they're all they offset each other because of the arrangement around the carbon. So remember, if you have we use kind of a hint, right? We say, hey, if it's symmetric, and you have the same atoms around it, well, then it's going to be non-polar. That's a nice little uh, tool to understand, but that's not a justification. The reason a molecule is non-polar is because the bond dipoles cancel. On the AP exam, if they ask why is this nonpolar, your answer is it's nonpolar because the bond dipoles cancel. And we can assume that every bond is polar unless they tell us that the electronegativities are the same or they are made, the bond is from the same type of atoms, right? So remember that right away, asymmetric, they're going to be polar. Molecules, and why is this? Because the bond dipoles do not cancel. Got it? So just remember that in your explanation. Bond, you can have a polar bond, but you can have a non-polar molecule right here, right? And so remember, polar bond is polarity within a single bond, uneven distribution within a single bond. Molecule, polar molecule, is uneven electrical distribution throughout a molecule. All right. Lewis structures. This should be a piece of cake to you, but don't get sloppy. Count your valence electrons, right? Count your valence electrons. Remember that carbon, nitrogen, oxygen, and fluorine are always going to follow the octet rule. Everything above that that has more electrons may end up with more than 8. So if you have sulfur or phosphorus or bromine or silicon or selenium, they may not follow the octet rule. Follow the rules of your Lewis structure, right? Count the valence electrons, choose a central atom, never hydrogen for your central atom, quite often carbon. Your F is almost never a central atom. So you choose your central atom and then complete your octets. Remember that my boron can end up with 6 instead of 8, and that your beryllium can end up with 4 instead of 8, and your hydrogen, you of course know, has 2. Don't forget on your structures, right? So count 4 and what is that? 16? No. 12, so a total of 16. Start off, complete your octets. Count 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. I have too many, right? So you start all over and you start doing your double bonds. 2, 4, 6, 8, 10, 12, 14, 16. There you go. So that's how you do that. Remember that. When you're making one other thing I guess I'd say about Lewis structures is watch how they write the formula. If they write it this way, they're giving you a hint on how they want you to write it. So you'd have a C with your H, your O, well, you may not know it's double bonded there, but you'd have an O and an O and an H, right? The reason they write it this way is so you kind of know the bonding that's going on, okay? So be aware of that. Formal charge. So because these rules in Lewis structures are pretty broad, there's a whole bunch of ways that you can create Lewis structures for molecules. Because I could have done this like this, right, ladies and gentlemen? I could have just said, hey, doesn't this follow the rules of Lewis, right? I have 16 valence electrons, carbons in the middle. I have 2, 4, 6, 8, 10, 12, 14, 16. So which of these do I use? These are both valid Lewis structures. Sometimes they'll say choose the one that's dominant using formal charge. And in this case, on formal charge, every atom has a formal charge, and you want ideally for every atom to have a formal charge of 0. Now, what is formal charge? Formal charge is equal to the number of my valence electrons minus 1/2 the number of my bonded electrons. I like to think of this another way. So if you're drawing your Lewis structures, if you're drawing your unshared pairs as unshared pairs, I like to think of it as just the number of valence electrons minus the number of bonds that are on my central atom. All right. So to give you an idea, so here we would start over here. This oxygen, I have valence of 6, and then I have 1 bond. So that's 1, 2, 3. Oops. 2, 3, 4, 5, 6, 7. So I'd have 6 minus 7. That's a minus 1, right? Going back to the carbon, I would have a 4. So this would be a minus 1. I have a 4 minus, I have these 3 bonds right here. So I'd count them as 1, 2, 3, and a bond here, 4. So 4 minus 4 is equal to 0. So my carbon would be a 4, or a 0. And then my oxygen here, I have a 6. And then I have what? These 3 bonds here. I'm going to count them as 1. One each line is a number, 1, 2, 3, and then I have these 2, 4, 5. So I'd have 6 minus 5, and that gives me a 1. So this oxygen is a plus 1. And so I'd look at this, and I have a minus 1, 0, and a plus 1. If I did it over here, I'd get 0, 0, 0. This would be the dominant structure, since the formal charges are all 0. Now, if you get something that is CO3 2 minus, you can't get a formal charge of 0. Your sum is going to equal the charge on the ion. If you have to have a formal charge on something other than 0, put the negatives on the atom that is the most electronegative. And just remember, I suggest that you know the electronegativity of 4 atoms, right? Maybe 5. F is a 4, O, oxygen is 3, 5. What's next to oxygen on the periodic table? Nitrogen is 3O, carbon is 2, 5, and then hydrogen is 2, 1. I just kind of know those. And the closer things are physically on the periodic table to F, the higher their electronegativities. Geometry. We can get our geometry. What is the shape of my molecule? Remember, the shape is based upon repulsions of electron densities around central atom. All my electrons that are around the central atom are negatively charged, and so they are going to do what? Repel each other. So the geometries minimize that repulsion, right? Now, we really talk about 2 geometries. There is the molecular geometry, which is the shape of the atoms, and then you can have an electron geometry, which is just what kind of arrangement do you have of electrons around the central atom, right? And these are all based on bonding domains and non-bonding domains, right? And we could have electron domains, which would be equal to these 2 added together. My bonding domains are the number of atoms directly bonded, right? And these would be my unshared pairs. Good. So try to remember this table, right? We could have what? 3 electron domains, and so that could be 2, 1, right? And so that would be bent. If you only have 2 electron domains, it's always going to be linear. I can also have a 3O, and this would be trigonal planar. I can have 4 electron domains, 4O tetrahedral. I should probably write these out. A 3-1. This would be trigonal pyramidal. You have your 2-2 bent. We have our 5s, right? 5-0. Trigonal bipyramidal. Trigonal bipyramidal, right? Oops, too far. I can't reach that high. Good. 4-1. This is what? This is my seesaw. 3-2. This is my bent T or T. 2-3. This is linear. And then we'd have our 6s. I could have a 6-0. And this would be octahedral. Octahedral. My 5-1 square pyramidal. And then 4-2 square planar, right? So now, if you want to know your, I guess we should put 2-0 up there, shouldn't we, to complete things? Gotta bring this. We have our 2-0 up here, right? 2-0 linear, right? So if we want to look at my symmetric arrangements, which will allow for my bonding dipoles to cancel, our linears, and then all of our O's, so trigonoplanar, tetrahedral, my trigonal bipyramidal, my linear, and my octahedral, and then my square planar. These are all symmetric shapes, and they allow for bond dipoles to cancel, assuming all the dipoles are the same, right? So that would mean if I have a carbon here, and if I have my my carbon with 4 hydrogens, those will cancel each other out, right? But if one of these or 2 of these or 3 of these are not hydrogens, but chlorines, for instance, then the bond dipoles won't cancel. And it doesn't matter if that's here or here, right? In reality, this is not 90-90-90, right? This is a tetrahedral, and so you would have 109.5 for your angles. Speaking of that, we kind of do need to know our angles, right? And so this would be for my linear. This is a 180, right? This bent. Well, let's get back to that in a second. Let's take care of the zeros. This is 120. This is 109.5. This would be 120 and 90? And then the last one would be 90-90, right? My octahedral, 90-90. And my square planar would be just plain 90, right? Now, those are the basic angles between my atoms. So if we look at something like this, remember, if you're drawing your Lewis structures, make sure you put in your unshared pairs, because you lose your point. When we're talking about the angle, we're talking about the FBF angle is 120. All right. Now, some things that have an effect. 2 things have an effect on those angles. One is if you have an unshared pair on your central atom. An unshared pair on your central atom is more repulsive than your electron domains, and so it will compress this angle. And so this is if this were a trig planar arrangement, this angle here is not 120, but less than 120. Now, if you answer less than 120, they would say, well, 5 degrees is less than 120. So you got to quantify that. It's not just less than. You can say slightly less than 120 degrees. All right. And another thing that will compress the angle would be a double or a triple bond. They do the same thing as they will compress those angles. So when we look at this bent, it's going to be slightly less than 120. When we look at this trigonopyramidal, it's going to be slightly less than 109.5. This bent, slightly less than 109.5. All right? My seesaw is going to be slightly less than 120, right? And my bent T slightly less than T. Well, my bent T looks like that, right? So that angle is slightly less than 90, okay? And so forth. Good. Anything else I want to say on this? Oh, over here. If they just ask for electron domain geometries, then you just look at these, right? And that would be linear, trigonoplanar, tetrahedral, trig bipyramidal, and octahedral. Now, don't give them that stuff unless they ask. If they ask for molecular geometries, then give them this. If they ask for electron domain geometries, then give them that. But don't confuse them or yourself with both unless they ask. Any questions on that? Okay. Resonance. Watch for resonance when you have a situation like SO3 2 minus, right? In that case, let's see, we have 24, 26 electrons, right? No, let's go SO3. SO3, you have what, 624 electrons, and so you'd say, okay, I can do this and this and this, right? And then we can complete our octets. Don't forget to complete the octet on your central atom, right? Now count. 8, 16, 24, 26. I have too many electrons. So then I would have to add a double bond, right? So I add a double bond, and now it's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So that's great, except for it doesn't make sense. It doesn't make sense that I have 3 SO bonds, and one of them is different than the other. We would expect that in that case that all the bonds would be the same, and that's when we use resonance, right? We would draw it all 3 possibilities, right? We'd put the double bond in 3 different places, right? We could put it up here. Oops. In here, and here, and then we do another one, right? So you put that double bond in all 3 possible places, and then you draw a line between them, and that says it's not any of these, it's the average of these, right? Now, one place where you always, the key is, okay, the key on this is they don't have to tell you to draw a resonance structure. They could just say all SO bonds are same, either same length or same strength. If they say they're all the same length or strength, you can't have one double and one single. So if they say they're all the same, and you have a double and singles, then you have to end up drawing it as resonance, right? Now that brings us to kind of bond order, and the bond order I like to think of as kind of like your average bond, right? So in this case, let's take a look right here. In this case, I have 3 SO bonds. One of them is a double, and 2 of them are singles. So I have 3. And I have a double and then 2 singles, right? So I look at this as 4 bonds, actually. We can think of it as, right, sigma, sigma, sigma pi, right? Here's a sigma, here's a sigma, here's a sigma, here's a pi. So I have 4 bonds over 3 bonding locations, which would mean that my bond order is 1.33. It's 1 1/3 bonds. It's the average bond. Okay, good. I think that's all I need to tell you about resonance structures. Hybridization. Hybridization, we have to do this when you have a central atom that's bonded to more than one thing. If I have 4 bonds, then I have to hybridize. We can't use atomic orbital overlap. Now, hybridization is easy. So we look at our, really, you look at your electron domains on central atom, right? Electron domains, and then from that, you get your hybridization. If you have 2 electron domains, so here's my ED, I have 2, 3, and 4. You're not going to be asked to hybridize more than that. If you have 2, the hybridization is, we call it SP, and there's 2 of those SPs. Now, we're assuming in every case that you have 1 S and 3 P orbitals which are available to be hybridized, right? So if I have 2 SPs, that would mean I have 2 unhybridized P orbitals. If I have 3 electron domains, then I'm going to go with sp2, and they're going to be 3 sp2s. And that leaves me with 1 unhybridized P. And then if I have 4, then it's going to be 4 sp3 hybrid orbitals. Okay? So you just, we take something like, this situation, right? We want to know what the hybridization is for my carbon. How many electron domains did I have? 1, 2. There are 2 electron domains. So if it's 2 electron domains, I'm going to hybridize that as sp. Now, here's the other thing. When we're talking about types of bonding, right? Any single bond we call a sigma bond, sigma, right? Any double bond is 1 sigma plus 1 pi. And any triple bond is 1 sigma plus a pi plus a pi. All right, so when we look at this kind of arrangement, we said that this hybridizes to sp, and the thing about it is my pi's cannot use hybridized orbitals. These need usually unhybridized p's. Now, you could use unhybridized Ds, but they haven't shown that on the AP exam in a long time. So, but you need unhybridized Ps, and that's why this kind of hybridization makes sense, because what I have here is I have a single bond, which is a sigma going to my oxygen. I have another sigma going to my other oxygen. Those are both going to be sp hybridized orbitals. And then I have my pi bond, and those pi's have to be unhybridized p's, right? So when you look at this hybridization, you get 2 SPs and 2 pi's, and that, 2 SPs, which allow us to have the 2 sigma bonds, and then you have the 2 unhybridized p orbitals, which allow for the pi bonding. Okay? Good. Now, the oxygens, doesn't matter what you do. If terminal atoms don't have to be hybridized, you can hybridize them, but they don't have to be. Last couple things. Last 3 things: bond order and bond strength. So the higher the bond order, as your bond order goes up, your bond strength goes up, and your bond length goes down. So now we have to compare the same things, but if we're talking about a single SO, a double SO, a triple SO bond, this would be the longest and the weakest, and this would be the shortest and the strongest. And so where would a 1.3 be? It would be right here, meaning a 1.3 bond would be shorter than an O bond, but longer than an S double bond to an O, and it would be stronger than an SO bond, but weaker than that. So that's bond order and bond strength. Bond enthalpies. But we can use bond enthalpies as how much energy is required to break a bond, a specific bond. And we can estimate our delta H by taking the sum of your bond enthalpies for all broken bonds in the reaction minus the sum of your bond enthalpies for all formed bonds. And so what you kind of have to do is draw your Lewis structure. So say we were taking CO plus Cl2, and we're going to form CCl, Cl, double bond O. Okay, I'm not going to put my electrons around. You should know that, if you drew this, you'd see that that's a triple bond. This is a single bond. And so when I'm doing my bond enthalpies, I actually have to draw my Lewis structures. And you have to watch your coefficients. If you have coefficients, you're going to have to multiply these by the number of, by the coefficients, right? And so over here, I already drew this. I have this, double bond that, Cl, Cl. Okay, so if I'm looking at this, what bonds do I have to break? I have to break that. So I have to break one CO triple bond, which happens to have a bond enthalpy of 172 kilojoules per mole, right? I have to break a Cl bond, and a Cl bond is 242. Now, what do? I'm going to form two CCl bonds. So I'm going to form two CL bonds, and a carbon-chlorine bond is 328. And I'm also going to form one carbon-oxygen double bond, and that would be 799. So my delta H would be these two added minus these guys. If it's a positive number, then it's more energy was necessary, so it's an endothermic reaction. If it's a negative number, it's exothermic. All right, so that is bond enthalpies. And the last thing, lattice energies. All right, lattice energies, we said at the very beginning, a lattice is formed between my cations and my anions, right? And a measure of how strong that is lattice energy. And lattice energies relate directly to coulombs, right? So if I want to know how strong a lattice is, we can look at Coulomb's law, right, which is the force between a positive and negative is equal to K Q1 Q2 over R squared. Now, when we're talking about lattice energy, Q1 would be charge of your cation. Q2 would be charge of your anion. And then my R's would be the sizes of my cation and anion. And the idea here is smaller gets closer, all right? So smaller ions get closer, meaning R gets smaller. Now, what increases my force? What increases my lattice energy? When Q1 goes up. So when my cat charge goes up, that increases my lattice energy. When my an charge goes up, that increases my lattice energy. When my R goes down, and what will cause my R to go down? Smaller. So what you're looking for, if you want to know what has the largest lattice energy, is you want big charges and small sizes for your ions. So for instance, we have NaF and we have NaCl, right? This is a plus, that's a minus, this is a plus, that's a minus. This is smaller than that. If that's smaller, that means my R is smaller, that means the force is greater, that means it should have a stronger lattice. And in fact, it is 910 kilojoules versus 788. So what they might do is they'll give you this and they'll say explain. And you'll say, hey, it depends on charge and size. They both have plus one, minus one, but the F is smaller the F minus is smaller than the Cl minus, so it's going to be stronger. And then you compare that to MgCl2, and it has a 2,526, right? And you'd say, hey, why is there such a difference here? Well, my Mg is a 2 plus, right? A 2 plus charge. And not only that, my Mg is going to be smaller. So my Q1 goes up compared to this, and my R goes down, and so that's why both of those increase my Coulombic force, and that's why that's that. All right, I hope that covered everything for you. If not, feel free to ask me questions. Good luck. See ya. Bye.